All right, hey everybody. Let's see here. There we go. Okay, hey. I just wanted to go over today how to interpret your NMR spectra for this lab. So it's a little quick presentation on how to use spectra from nuclear magnetic resonance, or NMR, um, to without any organic chemistry training. And so there's a lot to this technique that we're not going to go over. Because I just want folks to be able to use the data to interpret the results. And if you take organic chemistry, you'll learn a lot more about this. So um, proton NMR, or HNMR, gives us peaks that are going to allow us to follow a pattern as if it's a fingerprint for all of the hydrogens in a molecule. And so every molecule that has hydrogen atoms in it is going to give you a different pattern by proton NMR. And we can use those patterns to identify them. And if we have a mixture of compounds, we're going to get a mixture of those patterns. And so this comes from the fact that hydrogen atoms, the nucleus, has a spin to it, and that interacts with the magnetic field. And so we can actually look at the spin of hydrogen atoms and the energy associated with that spin flipping back and forth, and how much of a magnetic field it takes to sort of interact or lock onto them. And so let's look at an example of a compound. So here's the reaction we did in lab. You made aspirin. Here's the organic chemistry structure of aspirin. I know that this kind of like skeleton model is something we haven't covered in lecture, but it gives you an idea of the shape. We have a ring of carbon atoms here. We've got this carbon attached to some oxygens and a little hydrogen here. One thing that this structure doesn't show you is there's actually a bunch of hydrogen atoms attached to around this ring here that weren't shown. And then over here, this carbon has 3 hydrogen atoms attached to it too. So each of these hydrogens is going to give us some peaks, or up at least one or more peaks on our NMR data. And so if we look at pure aspirin, so we took a sample of pure acetylsalicylic acid, or aspirin, so not from this lab, but just actually store-bought stuff. And we get a signal that looks like this on the NMR. And what I want to draw your attention to is over here, the position of the peaks is what's important. And you see on the x-axis, you see there's no y-axis information. That's because y-axis is kind of not very useful or meaningful in these data. It's the location of each peak in the left to right direction along the x-axis that matters. This field in parts per million down here for our x-axis tells you how shifted each of these peaks are, or the little clusters of peaks, and each peak or little cluster of peaks is a hydrogen atom. This stuff over on the right, not so useful. So what I'm going to do is I'm going to zoom in here in this cluster on the left, which is more what we say downfield. Notice that the scale goes backwards. So it starts from 0 on the right and counts up. So we're looking at this region that goes from like 6.5 to 8.5 here. Now, when we look at this region, we get this fingerprint or pattern associated with aspirin. And which one of these peaks corresponds with which hydrogens in the molecule is beyond what we're talking about today. Just notice that we have this pattern of this one really big peak. It's what we call a singlet. It's one peak. It's not split into these like multiple little peaks here. It's just one singlet, one single peak at 7.25. So notice, of course, we're counting backwards here. So it's to the right of 7.3. That makes it 7.26. And then we've got this triplet of doublets. In other words, these little peaks seem to be split into 2, and then it's split into 3 here, and we've got another cluster of peaks here, another cluster of peaks out here. The locations of these peaks in the left to right on the x-axis is what we're paying attention to, and that's what we're going to compare. So what does salicylic acid look like? If I take some salicylic acid straight out of the bottle, it looks like this. So it looks different, right? There's something different going on here. And specifically, let's look at this pattern here. This is the downfield area associated with this aromatic ring here, which is what's going to give us the most information to tell these apart. Now you can see that this pattern is different. this peak here is actually the same. Look at that, 7.26. It's in exactly the same spot, and it's a singlet, meaning it's a single peak. And then we've got these other little clusters of peaks here. We've got one at between 7.5 and 7.6, and we've got one between 7.9 and 8, right? And then we've got this other cluster here that looks totally different between 6.9 and 7.5 or 7.15 or something, right? All right. So aspirin, salicylic acid, aspirin, salicylic acid. They're different, right? One thing I'm seeing right away, aspirin has, to the left of this 7.25 peak, has 3 clusters. So salicylic acid, to the left of the 7.525 peak, has 2 clusters, and they're in different places, different positions. So if you see this doublet for this cluster here to the left of 8.1, that only happens in aspirin. In sorry, jumping around. In salicylic acid, there's nothing to the left of 8.1. The doublet is over here to the left of 7.9. That change in position helps us to identify the difference between them. So it's really nice with NMR like this. We've got these 2 standards of this is what salicylic acid looks like. This is what aspirin looks like in the zoomed in downfield region here. You should be able to tell if you have one or the other or a mixture of the 2 by comparing your spectra to these examples. And I'm going to give you all of these spectra. I'm going to give you all these spectra when I send you your data. So good luck, have fun. It should be a quick little follow-up to see how well your synthesis worked.